Okay, we're going to start talking about turbulent flow, and I guess this first lecture is mostly going to be about just some conceptual sort of a picture of what turbulent flow looks like. This isn't a turbulence class. We will get into what the Reynolds averaged equations look like and some closure models for turbulence, but if you want to learn more about turbulence, you'll need to take a turbulence class. So today we're just going to get sort of started on what conceptually a turbulent flow looks like. And I guess the first thing to realize is that laminar flow can only persist for as long as the viscous forces in the flow are large enough to suppress turbulence, right? So this is our sort of conceptual picture of what a turbulent flow looks like. We talked about this kind of a lot. We have this laminar boundary layer, a momentum boundary layer that grows by diffusion mostly. There's molecular diffusion, not a lot of y velocity. So this is growing like the square root of time or the square root of x. And as this boundary layer grows, the viscous stress, which is proportional to the velocity gradient, must be dropping. So here's the increase in the boundary layer, the momentum boundary layer. As that boundary layer increases, the viscous stress drops like this. At some point, this viscous stress is not going to be large enough anymore to suppress turbulent eddies, and you'll go from a laminar flow to a turbulent flow. Right? And we can talk first of all about when that might happen. So we did talk when we were non-dimensionalizing our boundary layer equations. We talked about how the Reynolds number is related to this ratio of inertial terms or inertial forces to viscous terms. And it is related to that, but you should be clear that it's only proportional to that. It's not actually equal to that at all. This Reynolds number that we had defined is the given here. It's the characteristic velocity times the characteristic length times density over viscosity. For this flow that we're talking about here, this flow over a plate, it would be given by this equation here, right? So there is a characteristic Reynolds number based on this definition that delineates when you go from laminar to turbulent flow. It varies quite a bit, but something around 5 times 10 to the 5th, which is a really, really big number. A more physical Reynolds number in terms of what we're talking about here would do a better job of actually characterizing the inertial terms to the viscous terms. So let's think about what that might look like. So the inertial terms in a flow are rho u infinity squared. That's pretty easy. The viscous terms, though, the viscous shear stress is related to the velocity gradient, right? So if you go back and look at this equation, the velocity gradient is how much does the velocity change over this laminar boundary layer, right? So it's going to be u infinity divided by this boundary layer thickness. So if I want an accurate representation, or at least a physically realistic representation of the viscous terms, it would be mu times u infinity over delta sub m. So a Reynolds number then that would more accurately capture the ratio of the inertial terms to the viscous terms would be this term here divided by this term here, which is given here. And if you cancel out the u infinity, you see you have a Reynolds number that's based not on some characteristic length, but rather on the size of the momentum boundary layer, right? And so this is called RE, and the subscript means it's based on the size of the viscous sublayer. So this is my definition. Still dimensionless, it's just the characteristic length that I use here is not one given in the problem statement. It's rather it's the size of the viscous sublayer. So if we use this Reynolds number as a more realistic indication of the ratio of these two terms, what you'll find is that the onset of turbulence typically starts around a critical value of this Reynolds number that's on the order of a few thousand, right? Often 3,500 is used, which is, by the way, not coincidentally very close to the Reynolds number associated with turbulent flow in a pipe, right? And we'll get back to why that is the case. So this critical Reynolds number then basically says there's a critical value of the momentum boundary layer thickness. So this laminar boundary layer thickness is going to grow, but once it gets to some critical value, which we get by sort of solving this equation for delta sub m, at that point, the viscous shear stress is dropped so low that we get a turbulent flow, right? And of course, we draw this as being some kind of sharp transition from laminar to turbulent. In fact, it's not, right? There can be this transition region, and this is a much messier kind of a situation than what we like to maybe describe it in textbooks. But certainly there's a laminar region for sure, and there's a turbulent region for sure, and they're delineated by this critical momentum boundary layer thickness. If I want to think about this in terms of the Reynolds number that I'm more familiar with, it's a relatively easy thing to translate between those two, right? So when we were talking about our sort of conceptual model of how this laminar boundary layer grows, we said it grows like sort of the square root of not alpha, but nu, so kinematic viscosity times time, right? And sort of moving through that, we got to this kind of a scaling where we had a 2 here. If you take the exact solution, you get a 4.916 here. So if I use the exact solution, I find that this delta sub m is related to the Reynolds number defined in terms of x. And if I just take this equation and substitute it up here into my critical Reynolds number, right? So as long as I haven't transitioned yet, this equation is valid. I can do a little bit of algebra. So here's my Reynolds number defined in terms of delta sub m. All I'm doing now is solving this equation for delta sub m and substituting the result here. And if you do that, you find you have 4.916 times the Reynolds number divided by the square root of the Reynolds number. So 4.916 times the square root of the Reynolds number. Or if I solve for this Reynolds number, I find is 0.041 times the Reynolds number based on delta sub m squared, right? So I can go between a Reynolds number based on x and a Reynolds number based on the momentum boundary layer thickness using this equation here. So if my critical Reynolds number based on the momentum boundary layer thickness is 3,500, right, then if I want to know what it is based on the position x, you just substitute 3,500 into here and you get what you're probably more familiar with, which is 5 times 10 to the 5, right? So the Reynolds number based on x, the critical value of that would be 5 times 10 to the 5. So, if we do the same kind of thing here, this is our critical Reynolds number based on x is 5 times 10 to the 5. This is going to give me then a critical x position at which I become turbulent, which I can solve for. So, however you want to think about it, there is a spot on this plate where I'm going to go from laminar to turbulence. And at that point, the flow becomes very, very different. The laminar flow, sort of the basic way to think about that is everything is highly ordered. If I have a flow where none of the boundary conditions are functions of time, and I introduce a probe, an accurate probe into that flow at any location, so here at location A, I'm introducing a velocity transducer, and I measure velocity as a function of time. So here's velocity at location A as a function of time. What I should see is that the velocity is completely steady, right? There's no unsteadiness in that flow because it's a laminar flow. On the other hand, if I go over here and introduce a velocity transducer into my flow in the turbulent boundary layer, even if the boundary conditions of the flow are steady, nothing is going on that's transient, what I'll see is that the velocity recorded by that transducer varies quite a lot as a function of time, right? So there's going to be all these oscillations over a range of time scales, relatively large magnitudes, right? Maybe 10 even higher percent of the average velocity, and that's because the flow has gone from being this highly ordered, very logical, there's no deviations in the streamlines, right? Sort of a situation to over here I have a flow that the streamlines are changing all the time. It's very stochastic and very random almost, right? So you almost have to see this to understand what it looks like. So I tried to find some videos. So here's one that I think is relatively nice. So let's see if I can get this one up. So I'm just gonna play this one. It's 2 minutes and 30 seconds, and I don't think that's too much. So you can look at it, and I think it shows nicely the difference between turbulent and laminar flow. So I hope it was pretty obvious that when you watch that video, if you have laminar flow, you have these streamlines that don't deviate from being, in the flow direction, and therefore the transport of energy or momentum or whatever perpendicular to that flow direction. So in the y direction, it's almost entirely due to molecular diffusion, right? If you look again at that video during the laminar regime, you can see these fluid layers are not mixing, and therefore if I want to get energy from below this layer to above this layer, the fluid motion itself is not helping me at all. I am going to have to use conduction, right? So molecular diffusion to get to get energy or momentum to move across this flow stream, right? And so molecular diffusion is going to be characterized by the molecular properties, which are viscosity and conductivity, right? So this is kind of an interesting thing to talk about. When you start thinking about diffusion, when you start reading books about diffusion, you'll start to see people delineate between molecular properties and turbulent properties. And so molecular properties really just means the properties as we're used to thinking about them, right? So the properties that we talk about all the time are properties that characterize how the energy carriers and the momentum carriers in the fluid are behaving, right? We spent, I think, lecture 1 talking about how, conductivity is really this property that captures the aggregate behavior of all these different energy carriers that are operating together, right? So for a fluid, those are molecules, right? And so the conductivity then is sometimes called the molecular conductivity because it's capturing how all these molecules are acting together to move energy around, right? So that's what molecular means, right? And we're going to start thinking about turbulent properties, which are totally different, right? They are not capturing what the molecular energy carriers are doing at all, right? So when we think about these boundary layers in a laminar flow, they're growing according to these, very approximate equations, but this is a molecular viscosity and this is a molecular conductivity because it's the molecules that are bouncing into one another to move the energy and to move the momentum. If we switch over to thinking about turbulent flow, it's not that this molecular diffusion process doesn't happen. It certainly still happens. It's not that important anymore because it's not the dominant mechanism. Right? When we have a turbulent flow, if we go back and we look again at that video during the region where the flow is behaving in a turbulent way, what you see is that fluid packets are moving up and down all the time, right? They're moving up and down, and that motion of these turbulent eddies is really dominating the transport of momentum and energy, right? That motion is a kind of a superhighway in terms of taking energy from, one spot in the duct and transferring it either closer to the wall or farther away from the wall. You can take a packet of energy, right? A packet of fluid mass that has, however many billions of molecules in it, and you can move it very rapidly, across the duct. And that's just so much more efficient than asking those same molecules to bump into each other to get that energy to diffuse across the duct. So that's the dominant mechanism for energy and momentum transport in a turbulent flow, right? You have these turbulent eddies. And one way people like to think about this is that these turbulent eddies, they tend to increase the effective viscosity and conductivity of the fluid, right? Because not only do you have molecules bouncing into one another, which would give you the molecular properties, but now you actually have big packets of fluid moving around, and that's giving you turbulent viscosity and conductivity. So this turbulent viscosity and conductivity, so here if you see turbulent conductivity, it's going to be a lot bigger than the molecular conductivity. And by a lot, I don't just mean like a couple orders of magnitude. I mean many orders of magnitude bigger. And the same thing here for viscosity. The turbulent viscosity will be many orders of magnitude bigger than the molecular viscosity. So now, here we had a flow governed by molecular properties. Here we have a flow that's basically governed by turbulent properties that are much, much larger. They're much more efficient at transporting energy and momentum than a laminar flow is. So you're going to see, for one thing, the turbulent boundary layer grows just dramatically faster, right? Because now it's the turbulent viscosity and the turbulent conductivity that are going to push this boundary layer out. And that's true everywhere inside of a turbulent flow except for one place. And that place is called the viscous sub layer. There's this region very, very close to the wall, and it's a very, very thin region, hundreds of microns, where the presence of the wall itself and the large viscous shear that you get because the wall is there is sufficient to suppress turbulent eddies, right? There's no turbulent eddies in this region near the wall, and that's basically what defines the viscous sublayer, right? For one thing, the turbulent eddies just don't have room to move. They're constrained by the wall. So you think about this as a region then where you don't have a turbulent flow anymore. You're back to having a laminar flow. You're back to a region where the effective fluid properties are approaching the molecular fluid properties, versus out here in the core, the effective fluid properties are closer to the turbulent fluid properties.